Oh, thank you. That's much better now. Not great. Is that okay? Yeah. All right. Anyways, let's have a start now. So, let's have a look at the first statistics question. I think the statistics it's okay, it's not too bad, but some of it can be weird. Actually, what would be helpful is if we open up the formula book. Do you actually have a formula book with you? No. You know that there is a formula book, don't you? Yeah, okay. I'll just open it up here for you. Science formula book. Okay, so let's have a look at the first one. The ages of 7 children and 1 adult are shown below. Find the mean and the standard deviation. Okay, I don't think we need the formula book for that one. Which one is the mean? What do we have to do for the mean? Yeah, so here the mean would be 6 plus 7 plus 8 plus 8 plus 10 plus 11 plus 12 plus 42 all over, how many did we have? 8. Now, before you work out the answer, it's very, very good to just have a rough answer in your head. So what would you say would be a rough answer here? What would you think? Just roughly. What? 13? 20? I would say roughly maybe 11 or 12. Roughly 11 or 12. In other words, if I got an answer of 52, I know I did something wrong. That's my point. It's good to have a rough idea. Okay, so if we bash that into the calculator, what do we get as an answer, please? 13. Exact? Alright, okay. Now, the next one, the standard deviation. There are 2 ways to calculate this. Which one are you used to in class? What is the one what formula do you normally use here for standard deviation? Now, I can open the formula book up if you want, but what formula do you use in class? Which one? Over n with a square root? Yeah. The 2 choices you have are, you can use this formula. Standard deviation equals square root the sum of the data minus the mean squared over n. Okay? But the second formula, which I think is a little bit easier and a little bit quicker, is this one. Standard deviation squared equals, now let me just make sure I remember this correctly, x squared, and it's the mean of that, minus x mean squared. Now this one here I think is a little bit easier to use than this one, although both will give you the same answer. I'm going to show you how to use this one, and I wonder actually what they have in the formula book. Let's see. What page is statistics? Calculus. Now, it looks like they kind of go with both. This is the formula I just wrote down. And this is the one as well that you probably are more familiar with. They both actually give you exactly the same answer. Okay, so let's use this formula here. this I don't know, and this one I just worked out. It was 13 squared. Now, can anybody tell me what exactly is the difference here? I mean, they look like the same thing, but there actually is an important difference. Can anybody see what it is?
It's the number of values for
Yeah, which one now?
the first one.
The first one? Yeah, that's it. Just be very careful. Here, first I square, then I average. Here, first I average, then I square. So let's calculate this. I would just have to change this here, actually. If I wanted this, I would just have to go square, 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 square. And then I have this number here. I think I have my calculator, so let me type that in. Here we go. Whoa, okay. Right. Over 8. Okay. 6 squared plus 7 squared plus 8 squared plus 8 squared plus 10 squared plus 11 squared plus 12 squared plus whatever 42 squared is. 1171 over 4. 292.75. Okay, so now I have sigma squared equals 292.75 minus 169. Okay, so now I've got my answer. Minus 169 and square root to finish. Square root my answer. And I'm left with 11.1. So, I don't know what you think. Any difference you feel between the other formula? It doesn't really make a difference. This is harder, this is easier. What do we think? It's a little bit easier, I think. It's a bit annoying actually because this question's only 3 marks. It's only 3 marks. I feel like it's more like 4 or 5 marks. Anyway, let's go on to the next one. Can I scroll down? Yep, okay. So the next statistics question here. In a chemistry experiment, acid is added to 10 different amounts of an alkali until neutrality is reached. The amount of alkali is the X and the amount of acid is the Y. Calculate Sx, Sy, Sxy. So in our head what we've got is something like this, X and we've got a Y. And I kind of feel like, well, I don't know, you all study chemistry. Well, no, actually, even I know this. If it's more alkali, you'll need more acid to neutralize that, yeah? I haven't mixed up my basic chemistry. This is correct? Alright. So, if the X is bigger, what do I expect the Y to do? Be bigger or smaller? It should be bigger. So, I think my graph will look something like this. And I'll have a straight line. By the way, what's the name of this type of graph? Very good, yeah. Scatter plot. Yeah? Okay, now, the good news is the formula for what the Sx is actually in the formula book, I believe. If we just flick to the formula book, here we go. Let me zoom out a little bit. Can you see the Sx here? So what this means is you multiply the data and add it up and divide by the number of points, and then you minus the average X times the average Y. Now you might say, oh, but I don't have the data. How am I supposed to do this? Well, this is actually very good news, because in the question they actually provide you with this. What is it? It's 7696. So this is 7696 over n 10 minus. Now, not too hard, but we actually don't know the average x and the average y. But we could easily work it out from the data that they gave. How could I work out the average x? What would, yeah, it should be what exactly? 260 over 10. Now, can you see why I'm saying that? It's because you add up all the x's and divide by 10. And so what would be the average y? 293 over 10. Can you all see that? Yeah? This here is add up the y's and divide by n. This one here is add up the x's, divide by n. This one here is add up the x's and the y's, divide by n. Right, so let's bash this into the calculator. 769.6 minus 26 times 29.3, and I get 39 over 5, 7.8. Actually, what did I work out there? That wasn't SX, I don't think. That was XY, okay. Right, so I still have to get SX and SY. Okay, back to the formula book. Do I have the formula for SX? I do. It's square root this one. Do I know this one? I do. It's 6844. Okay. So that's square root 6844 over 10 minus this I now know. What did I say? It was 26, wasn't it? Minus 26 squared. And then the other one will be just with the y, I guess. What's that? 293. No, it's not. It's, what is it? 8682 over 10 minus 29.3 squared.
Will we be given the data on the usual basis in the exam?
You mean like this?
Yeah.
I would say it's very likely they will provide this, although not guaranteed, but quite likely. You realise that it's much nicer when they do give you this rather than having to count it up yourself.
Yeah.
Much nicer. Okay. Can somebody bash the first one in while I'm bashing in the second one? So, let's see, that's square root 86. You have the first one? 2.898. So, if I round that up, that would be 2.90, I think. Yeah. 2.90. And then the next one, 3.12? Yeah. Okay, that's not too bad, but it's only 3 marks. Well, you know, it's not too bad, but it's not too easy, I guess. The next one is use your answer to calculate the correlation. Again, this should be in the formula book. Where is it? There it is. It's SXY over SXSY. So, what letter do we use? It's or, isn't it? Yeah, that's what I thought. Or equals 7.8 over 2.9, 3.12. Okay. No, it's not, because, well, I suppose technically it's okay here because this is the rule in the exam in case you're wondering. Your calculations must be to 4 significant figures and your answer to 3. Because this question here, because these are answers, I'm allowed to use it to 3. But let's just imagine for a moment that this question didn't finish and start a new question. Let's imagine instead of part 1 and part 2, it was just part 1. Then because these are actually calculations, I must use at least 4. But because I've started a new question, I feel like it's okay to keep this at 3SF. Question? Go ahead, Joe. No? Okay, what do we get here if somebody's typed that in already? 0.862. Now they often ask for a comment. Do they ask for it here? Yeah. So what is the comment you would make here? And positive. Yeah. So you would say a strong positive linear correlation. It should get you the 1 mark, and then 1 mark here. I would say 1 and 1. Okay. Have you all actually? What are you doing in maths class at the moment? Oh,
I don't know.
totally lost.
Yeah. Doing
Not knowing the name of your chapter you're doing is worrying. It's statistics for sure. Okay, but what part of statistics? Expected values and variance. Okay. So you've already finished the correlation and the scatter plots then. Yeah. Okay. Right. Can we go on to the next one now? Yep. So the height of 50 trees were recorded and the results are shown below. You may wish to copy your answer booklet and extend this table. Estimate the mean and where does the median lie. Now, before I do this, since you're still working on statistics, of course, have you done this type of problem yet? Yeah, so it says estimate your mean because you can't actually get the exact answer. Why can't I get the exact average height of the trees? What's stopping me from getting the exact average height of my 50 trees? Yeah. You don't know because the heights are between ranges. So, for example, how many trees are between 3 and 3.5 meters? Well, there's 6 of them, isn't there? But what height are those trees? Well, we don't know exactly. So what do we use when we don't know? Which one? Yeah. So, I mean, what height should we use for those 6 trees at the beginning? So if I want the average height, okay, I know that everything will be over 50, right? What's the first tree? The height of the first tree? Is it 3 meters? Or 3.5 meters? Or something else? In the middle, yeah. So what should I use? I should use 3.25, yeah? Now, how many of these trees do I have that are 3.25, roughly? 6. So I'll just write etc. And I have 6 of them. Okay, on to the next group of trees. What height are those? 3.75, yeah? And how many of those do I have? Whoops. Etc. And I have 10 of them. Etc. So I hope you can see the pattern here. What I'll end up getting is 6 times 3.25 plus 10 times 3.75 plus 18 times 4.25 plus 12 4.75 plus 4 5.25 all over. Now, before anybody tells me the answer, again, we should estimate so we can at least know if we're roughly right. So very roughly, don't cheat and give me your guess if you've worked out the answer. So if you haven't worked out the answer, what would you estimate the answer to be? Anyone want to give me a guess? This is your chance to guess in maths and be wrong, and that's okay. Average height 0.5? I think it'd be more than that. Because the smallest tree is 3 meters, and the biggest... Yeah. I would say, yeah, I'd say something like 4.2, kind of early 4s. Alright, so let's... Somebody surprise me. What is the average height? Did anyone type it in? Oh, I'm so good at guessing. 4.23 meters. Yeah.
Can you just add up the first one, which is 3.0, and the last one, 5.5 divided by 2?
For estimating? Yeah.
It's 4.25.
Yes. Well, I did something similar in my head, but I was kind of mindful that if you look, there's slightly more smaller trees at the small end than there are larger trees at the large end. So that's why I said 4.2 rather than 4.25 for my estimate. It was only an estimate, you know. So if you took both our estimates and averaged it, it would be even better. Because that would have been 4.225. It's even closer to the real answer. But the reason I tell you to estimate before you get the answer is because it's really good in the exam to know if the answer you just got is like a reasonable answer, that you didn't get something crazy. Because it's so easy to mistype on the calculator, you know. You want to make sure you got it. Okay, the next part is the median. So this is actually the mean. What's the median? I mean, what is the meaning of median? The middle value when you rank them from minimum to maximum. So if I have 50 trees, which number in the list of 50 is the middle?
25.
It's between 25 and 26. So it's somewhere between the 25th and the 26th height. So, if I look at the first box... Oh, sorry, can I scroll down? Yeah. So if you look at the first box, you have the small trees. That's a tree. You have the first one, the second, etc., etc., up to the 6th one. These are all the 6 small trees. Now, when you go into the next box, you have the 7th tree, if we're going from small to big, and the 8th, etc. And what's the last tree in this box? Oh no, I tricked you. I got you. The 16th. Can you see why? Yeah, because I already have 6 from the first box, and I have 10 more. Yeah. Okay, so in the next box, I start on the 17th, and I finish where?
34.
Is it 34th?
Yeah.
Okay, so I stop. Because I know the 25th, 26th tray is somewhere in this box. So the answer is in the... 4.5, isn't it? Range. Anyway, there's only 1 mark, so it's not supposed to take you too long to do.
What if they ask you what the median is?
Say again?
What if they ask you what the median is?
What would you say? I'll go on. Give it a go. What would you say? Oh, okay, fair enough. The median is the value in the middle when you rank from minimum to maximum. So I'll write it down for you. The median of a data set is the middle value when ordered from min to max. So if you have x min all the way up to x max the median is the one
Yeah.
in the middle.
But for this question, like we know the interval that it
Oh, what would you estimate as the actual value? Good question, which they could actually ask. Does anybody have an idea on how we could tackle this? How would we estimate the median? So, like, just go back up here. It's a very good question, actually. And how would you estimate the median here? Does anyone have a strategy or an idea on how we could kind of figure this out? Well, we know something. We know that it must be from 4 to 4.5. So what value could we pick? We could pick one in the middle. So we could estimate it as being 4.25 perhaps, yeah? Although you then realise there might be a small problem with that. Let me pretend for a moment that the median was the 17th number. So if the median is the 17th number, is that number likely to be nearer to the 4 or nearer to the 4.5? Yeah, because it's just about in this box if it's the 17th. Yeah. What about if I said it was the 34th was the median? Then it's likely to be nearer to the 4.5. In this case, I got, what was it, 20, 25, 26, wasn't it? Okay, so let me just draw this out for you. 17th, 18th, 19th, 20th, 21, 22, 23, 24, 25, 26, 27. How far am I going? 28, 29, 30. I regret starting this now. 31, 32, 33, 34. Okay, and if it's between 4 and 4.5, we kind of think this guy here, he might be a 4, and this last fella here, he might be a 4.5. And where are we? We are, is that exactly in the middle? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ah, it's bang in the middle. So 4.25 would be an excellent estimate for the median. 4.25. Obviously, if it was something like here, then it would be the middle of this half. You would say maybe it's about 4.1, 4.2. Because it's an estimate, you're allowed to be sort of a little bit off. Okay, are we happy with this one? Can we go to the next one? Yeah. Now, I know you said you're doing it in class right now, so do you think you've done enough of expectation and variance to do the next one, or for me to do the next one, I should say? Do you feel like that's something you should be able to do? Have you seen tables like this before?
Yeah.
So, do you know off the top of your head what is the formula to get the expected value of x here? Yeah, what is that now? Expected value of x. The sum of p times x. Yeah. Over. No, sorry, not over. Sorry, just sum p times x. Okay. So that is 0.08 times 0 plus 0.15 times 1 plus 0.2 times 2 plus 0.22 times 3 plus 0.19 times 4 plus 0.16 times 5. Okay, if somebody can kindly type that in, please, that would be great. Now, before anybody gives me the answer, let's estimate. So have a look at that table. How many different values are there of x? Well, technically 6 actually, if you count 0 as one of them. Now, I feel like the expected value should be something like, let's go with 2.7 is my guess, my estimate. So what is the actual value, please? Oh, I'm on a roll. 2.77. Good. Now the next one is a little bit harder. Have you done variance? Yeah. Now the formula for the variance of x is the expected value of x squared minus the expected value of x, and then that is squared. This kind of looks familiar, doesn't it? Where have we seen a formula that looks a little bit like this? Doesn't it? Doesn't it look like the same formula for the sigma? Because we said sigma squared is the average of x squared minus the average of x then squared. Can you see the similarities? This one is first you square the x, then you get the expected value, minus first you get the expected value, then you square. Okay. So let's work this out. This we don't know, but this we do know. It's minus 2.77 squared. Right, how can we get this? Well, we actually just have to go all the way back up here and just square all of these. Square, 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 and square. You have it, thank you. What is it, 9.97? Okay, so what do we get here if we were to minus those two? Should be something like about 5 or what is it? Like, hit that in then. 9.97 minus 2.77 squared. 2.3 roughly. Yeah. If I round it up with 7, yeah. 2.3 roughly, yeah. Just so you know, the variance is always positive. In fact, it's impossible for it to be negative. Impossible. So if you got a negative value, it means you've typed in something wrong. Okay, it has to be positive. Has to be positive. Okay. Now, there's a second part here. I'm not sure if you've done this part. Can I scroll down a little bit? Yeah. So, just before I scroll down, let me just write down my two results. Expected value of x is 2.77, and the variance of x is 2.3. Right, part 2. What is the expected value of y? And y is defined as 3x plus 5. Now, have you seen this type of problem yet? No, you haven't done this type yet. Well, you'll probably do it quite soon, so I might as well just show you what happens here. You might say, oh, okay, so this isn't that hard. All I do is I take my x, I multiply it by 3 and add 5, and repeat the process. So if you go back to the table here, you just change all of these numbers. And that's fine, that would work. But there's actually a rule that you'll learn that saves you a lot of time. You might actually even guess the rule, that the answer here is 3 times the expected value of x plus 5. Now, think about this for a moment just before we work with that. Suppose I give you 3 numbers. Let's say, make it easy, 1, 2, 3. What's the average here, for example? The average here is 2. Yeah? Now, suppose I was to multiply all of these by 3. So I get 3, 6, 9. If I was to get the average here, I would get 3. But that's the exact same thing as taking the 2 and just multiplying it also by 3. So the point I'm making is, if y is 3x plus 5, then the expected value of y will be the same as 3 times the expected value of x plus 5. That whatever you do to the data, you can do the same thing to the expected value, and you'll get the same answer. Now, if you're confused, that's okay, because you haven't studied this one yet. I just want to give you the answer so that when you do study it, you have this example done. So that's 3 times 2.77 plus 5. Do we have what this is? Three times 2.77 plus 5. 41? Must have mistyped. 13.31 is what I got. Okay. And now the next part is the variance of y. And what do you think that's equal to, if you were to guess? Like, what would be the formula here? What do you think? Do something similar to this, is it? Yeah, you think perhaps it works the same way for variance. That the variance of 3x plus 5 is actually maybe equal to 3 times the variance of x plus 5.
Is it just
Yeah?
you just square the differentiation?
Oh, this one? No, actually, no. It's a little bit more to it than that. In fact, I think you might have the formula in the formula book. Yeah. Huh? This is a blank page. They don't give you all the formulas. Shame. Okay, anyways, I'll give you the formula. I'll write it down here. So just to be very, very clear, the expected value of ax plus b is equal to a expected value of x plus b, and the variance of ax plus b is equal to, and it's not actually the same, a squared variance of x. And no b. It doesn't actually affect the answer if you have a b or not. So you haven't seen these formulas, you'll probably... When's your next maths class? Tomorrow. And you just did this yesterday or something? Yeah, okay. So you'll probably see it tomorrow then. Right, so let's just finish this one. This will equal, can somebody type in 9 times 2.3? What do we get? 20.7? Alright. Have you done the next question yet? The chi-squared? Chi-squared. If you don't know what it is, it means you haven't done it. Here's the symbol for it. You're looking like you haven't done it. That's fine. I just want to check that I'm not skipping anything. Yeah. These are the faces of people who are confused. So you haven't done this. So we won't do the next question then, yeah? Right. Next page. Okay. The ages of 8 people are shown below in ascending order, smallest to largest. The average is 11. Find 2 possible values of x with a reason. Which of these values is correct? Yes.
The chi-square question.
You want to do it?
Yeah.
Even though you haven't studied it?
Yeah.
You're feeling brave.
I mean, it's because you probably explained it, but I don't think.
Well, I can do it, but I can do it. But I won't spend a tremendous amount of time on doing it. Okay. So let's have a look. before I do it, just to give you a tiny bit of background on when or why you would use the chi-squared, okay? So, here's an example. Let's say you have a coin, and you're flipping the coin, and sometimes you get heads, and sometimes you get tails, okay? So let's imagine I flip the coin 100 times. 100 flips, okay? How many heads and how many tails do I expect to get? Yeah. Heads, tails. I expect to get 50 and 50. Fine, okay, that's fine. Now suppose instead I got 100 heads and 0 tails. What would that make me think? What would I start to question? Yeah, in fact, I might even start to question if the coin actually has a tails. Right? What about if I got 99 and 1? What would I start to think? We think, yeah, what about 98 and 2? Again, yeah. Now what about if I got 51 heads and 49 tails? Yeah, so we all understand there must be some point that we cross, and when we cross that point, we start to get suspicious. So we're happy with numbers like 51, 52, but not 98, 99. So the question is, where do I draw that line? And that's what we use the chi-squared for. It's a way to test if what we expect and what we observe are quite similar or quite different. Okay? So, usually you make a table like this where you have expected values and then the observed values. So perhaps I observe 55 and 45. Okay, so this is the idea that we have. Right. So let's have a look at the example that they have. Can I scroll down? Yeah? Okay. So we have a tetrahedral die. A tetrahedral die is just a die with 4 sides. Okay. And how many times do they roll this die? 100 times. Okay. So you can get a 1, you can get a 2, you can get a 3, you can get a 4. Now, if I roll the die 100 times, and if it's fair, how many 1s do I expect to get?
25.
Yeah, and then here, 25, 25, and 25. Okay. How many 1s did I observe when I did this, according to the table? 21, and then 28, 19, and 32. Now, before we do any calculations, in your opinion, only your opinion, would you say this is a fair or unfair die?
No, it's kind of bad.
No, you see, this really shows you the point of the chi-squared. It removes your opinion so you can actually calculate for certain. Okay? But if I was to ask for your opinion, if you were to give me an answer and you had to choose, would you choose fair or unfair?
Unfair.
Hey, great. I love it when it's split. It's much more interesting this way. I think I would say...
It's more bad.
yeah. I would say to me, it's just about believable. Just about. But also, I might be wrong and it could be just about unfair. But let's see for certain, okay? So what we do, we write down our hypothesis. I'm sure you know this word, hypothesis. What would you say is the meaning of the word hypothesis? Doesn't necessarily have to be predict, but you're right, a statement, like a theory or like a claim. So the hypothesis that you always write down is the one that the default is that it's fair. Okay, so the default is always that you assume it's fair and then you test if it's fair. So our hypothesis is that it is a fair die. And now Let's test it. Okay, so the way we test it is we calculate something called the chi-squared. And the formula for the chi-squared is, if I remember, but it's in the formula book, we have to add up the expected minus the observed squared over the expected. Yeah, so let me just write that down again. We add up the expected minus the observed over the expected squared. So here that would be, let me see, 25 minus 21, 4 over 25 squared, plus 25 minus 28, minus 3. So that's 3 over 25 squared. Why did I not bother putting the minus down? It can be negative, but why did I not bother writing the minus? Well, I'm squaring it, so there's no point. The next one would be what? Tell me what the next one is. What would be the next one here? It'd be 6 over 25 squared, and then the last one, what would it be? 7, yeah. 25. Okay, can we calculate this, please? And then while you're calculating that, I need to open up the table book to get a table. What? Did you get an answer? There we go. Okay, what was the answer there when you add 0.176? Now, tell me this. Imagine that everything that was expected was observed. So this was a 25 and this was a 25. This was 25 and this was 25. That would be the perfect situation, wouldn't it? We definitely would know the answer. Would it be fair or unfair? It'd be fair. What would be the total here if that was the situation? If it was perfectly fair and clearly fair? 0. So, what do we interpret this number to mean? In other words, if this number is bigger, is that good or bad news? Bad. So there must be some limit where if it's too big, we say no, it's not fair. And we get this from the table. In the formula book, there's a table, I think it's on the last page. Okay? On the side here is called the degrees of freedom. That's simply how many boxes you have minus 1. So for this table, the degrees of freedom for this problem would be 4 minus 1 would be 3. So what you do is you go to row number 3. And we look at the 95%. Now, why do we choose 95? You don't have to worry too much about this. It's kind of like, do you know the word convention? Like standard practice? It's kind of standard practice to use the 95% limit. What that means is we're kind of 95% confident of our answer. Now, it doesn't exactly mean that, but roughly, very roughly it means that. So, at 95% and 3 degrees of freedom, what is the limit? What is the biggest number we're allowed to have? 0.352. So the limit, I'll write it as crit, for critical, is 0.352. So, is our result beyond this limit or within this limit? Yeah. So, do we reject this claim or not reject it?
No, reject.
Yeah. Do not reject. So, the people who said, we think that this is fair, congratulations, you guessed correctly. It seems to be fair, or at least we don't have evidence to think it's not fair yet. Do you notice in the question it says carry out the test at 5% significance?
Yes.
That 5% means to use the 95% box here. Okay. 5% is the most common standard percentage to use for these tests. It's used at university and in research papers. So it'd be very, very unusual for them to use a different percentage. Okay. Really, it should always be this. Okay. So before I continue, this is new. Is there any questions on this chi-squared? By the way, this is going to be part of your coursework too. Oh, you know this already. Have you seen the coursework too?
Yeah.
Okay. The genetics one.
Yeah.
Yeah.
I asked you.
Ah, very good. Okay, very good. All right. So in your genetics one, what would happen is, I think you have 4, whatever they're called. That's the word. 4 genotypes, and you have expected number of genotypes you should observe. Expected number and the observed number in your data, and you want to test if they're similar or too different. Yeah. What is it now? It's the plant, isn't it? With long and short, purple and red. Okay. Yeah. I should know this since I made it, but you know, I'm tired. Okay. Well, since you're doing this for your coursework, then I better make sure that there's no questions here. Are we all okay with this? Yeah? Okay. Right, let's have a look. Oh yeah, so just so you see here, part 1, state your hypothesis. That was here. Part 2, work out your expected values. Oh, well, that was easy. That was here. Part 3, carry out the chi-square test. That was everything else. So, this is 1 mark, this is 1 mark, and then everything else is 5 marks. Yeah. Okay. Shall we go on to the next one? Mm-hmm. Yep. All right. Okay, this one isn't too bad. They want to know what is the value of x, and we're told the average is 11. So we have 2 plus 3 plus x plus 8 plus 12 plus 16 plus 17 plus x squared over how many? 1, 2, 3, 4, 5, 6, 7, 8 equals 11. Can somebody type in, please? Well, maybe we can do it. No, that's dangerous. I'm asking for trouble. 2 plus 3 plus 8 plus 12 plus 16 plus 17. What is it? Okay, so on the top, I have x squared plus x plus 58 over 8 equals 11. X squared plus x plus 58 equals 88. X squared plus x minus 30 equals 0. And what are my 2 factors here? Plus 6 minus 5. So, x equals 6 or... See, sorry, I just realized how stupid that was. Thank you. Minus 6 or 5. Okay. Now they say, state the 2 possible values of x and state with a reason which of these values is the correct one. Say again?
5 is the right one because you're talking with ages and it can't be negative.
You're right, it can't be negative, but I can use minus 6. Tell me why I can use minus 6. Yeah. You see, whoever wrote this question, I feel, made a mistake that you just made. You forgot that the age of the last child is not x, but what? X squared. Now, if the age of the child is x squared, then we can have 36 or 25. However, we can't have two answers. That feels wrong. How could I have a 36 or 25 and both gives me the same average of 11? One of these must be wrong. And the reason that it's wrong is not because it's a minus. Like, it might be that this is the wrong one. So now we have a big problem. How can I know which is the right one and which is the wrong one? One of them has to be wrong. They can't both be right. That doesn't make any sense. Well, how could we check? Exactly. We'll try it, yeah. So, let's bash this in. Now, I'm feeling like we'll go with the -6. Test that out first. Can somebody just call out all the numbers so I can type them in? What's the first one? 2 plus... Yep. 6.
Why can't you just, if we're going to put...
Oh, sorry, I retract my previous statement. I forgot that the third child's age was X. I was only thinking about the last child. Yes, everything you said is right. Thank you. We cannot use the -6. No lunch. This is what happens when you have no lunch. So, reject -6, accept 5. Okay, good thing that third child was there and made it much easier to do. Right, I don't know, 5 marks is kind of a lot, really, isn't it? Like, all you had to do was solve a quadratic, ultimately. Solve a quadratic. Okay, have you done normal distribution? Yeah. Well, which is it, yes or no? Now, you know if you've done it because you would have used this page in the formula book a lot. Not this one, but the... Where is it now? It's at the bottom?
No.
Hang on, let me just zoom out. No, it's not that one. That's binomial, normal. You have not used this? No. You probably... Have you only been doing statistics so far, like averages and histograms, and you've not done any probabilities in semester 2?
In terms of probability,
yeah.
I've done the expected.
That's okay. So you haven't done normal distribution then. Okay. Right. So we'll look at the next one then. Well, actually, yeah, the next one is correlation. It's very similar to the first example that I did, but they're asking you for something extra that we didn't have last time. If you have a look at the next question, what is the extra thing we have to do this time that we didn't have to do last time? Oh no, sorry, the next one. We're going to skip that one because you haven't done it yet. So the next one, with the temperature, the table. So in the next one, what you have is, in a biology experiment, the rates of water loss were measured in 6 plants. The plants had similar leaf area, and the results are below. So this is the temperature, and this is how much water was lost per minute.
You have to find it at a certain temperature.
Yeah, and even before that, they want you to find the equation of this line. Yeah? So, anyways, let's just do the first part. First, let's calculate Sx squared. Well, first let's calculate Sx, and then we'll square it. So, Sx is square root, if I remember my formula, is it 2276 over 6 minus 114 over 6 squared. Is that the formula? I think it is. Let's just double check it. There we go. Maximum zooming in. Okay, so Sx is square root x squared over n, yeah, that's it. Okay, can somebody type that in, please, and tell me what you get? And then I'll just write down the next one. Did we get this? $4.28, and then could you hit the square button to give me it squared, please? What is it? 16 point something? Come on, guys, don't make me work so hard. I'm tired and hungry. Just square this and tell me what it is, please. 18.318. Thank you. So kind. Had mercy on me. Right, Fxy. And here's the formula for xy. So, on the top we have 723.1 over 6 minus 114 over 6 times 36 over 6. Okay, please type this in and tell me what you get. $6.51. 5152. Thank you. Okay. Now, that answers part 1. Part 2, find the equation of the line. And again, the good news for you is that you have the formula in the formula book. Let me show you where it is. You see this formula here? This gives us the equation of the line. So we have y minus the average of y. Okay, so let's write that down. Y minus the average of y equals Sxy over Sx squared. Now, can you see why they had us calculate this? Because we need it for part 2. So that would be 6.52 over 18.32. X minus the average of x. Average of x is 114 over 6. Okay, so I just need somebody to give me this fraction, please, as a decimal. What is it? 0.36. And is this a decimal as well? 6? 19. Nice. So that's y minus 6 equals 0.36x minus 0.36 times 19 is going to be something for sure. What is it? 6.84. Okay, so that means y equals 0.36x minus 0.84. No? Ah, but this guy comes over. Yeah? So, is that okay? Yeah. Now, what has this done? We have a formula that gives us, well, what's the y for this question? What does the y represent? Yeah, this bio thing, whatever it is. And the x, temperature. So you can kind of see the relationship here. What happens as the x increases? Well, obviously we can see that the y increases. In fact, if the x was to increase by 1 unit, how much would the y increase by? What do we think? If I was to make the x 1 unit bigger, what would happen to the value of y? How much bigger would it be? No, it wouldn't be 1 unit. No, just how much bigger, not what would it be, just how much more would it be. Confused? My question confused you? No problem. So, you know when you have a line, y equals mx plus c, and I say the m is 2. What is the meaning that the m is 2? What does that mean on the graph? Yeah, and what does that mean? Like, what is the slope of 2? What does that mean? Yeah, if the x goes up, if you increase the x by 1 unit, the y would increase by 2 units. So if I increase the temperature by 1 degree, my temperature goes up by 1 degree, what is the increase in the whatever the other thing is? 0.36. Because the slope is 0.36. Now the reason I'm telling you this is because they sometimes ask you to comment. I wonder if they did that here. No, not this time, but maybe next. Right, part 3. Estimate the transpiration rate when the temperature is 30. Alright. Y equals 0.36 times 30 minus 0.84. What's that, about 10 or something, is it? What do we get here? We just bash that in. That's part 2 now. $9.96. Man, I should play the lottery tonight because I'm just guessing so close. 9.96 now. Okay. Milligrams per minute is the unit. Alright. Part 3, the final part here. For 2 marks actually. So for 2 marks that means they want an answer and a reason. Is your answer in part 3 reliable? In other words, is this value that you predict for the y at a temperature of 30 degrees, is that a reliable prediction? What do we think?
Yes.
We have yes and we have no. Wonderful. So if the person who said yes has a reason and the person who says no has a reason, so you're saying yes, it is reliable, and the reason you would give? Good, okay, so you would say yes because it's not too far away from the actual big temperature, 25. And the person who said no? By the way, I'm not totally convinced that the answer is clear, that there's clearly a right answer here. So I would see both answers as being possibly valid. It depends on your reason. So your reason of yes, because it's not too far away from the upper value, is reasonable. But who would say no, and what would their reason for no be?
I think 30 degrees is a big difference from 21, because I know that the rate of transpiration should be a lot higher.
Yeah. So I would actually agree with both people. But if I have to choose, it's hard because 30 degrees is not far away from 25. Still pretty far though. I feel like I would finally choose no. And the reason I would choose no is because I think 30 is just a bit too far away from 25, which is the biggest point you have in your data. So we have our graph, we made our line, and then what we did basically was, over here at 30 degrees, we predicted what value we would get. What did we say? 9.96. But I do feel that our 30 is a little bit too far away from our data. Because as biology students, you probably know that the linear relationship, it's not going to stay linear forever. Like at some point when the plant gets so hot it dies, and I imagine it stops transpiring when it's dead. Would that be reasonable to assume? I would think so. Dead plants tend not to transpire, right? So, if you were to really think about this graph, what might its true shape be? So it would increase, but then if you make the temperature even higher and higher, it'd probably start to go back down, would it? And then it would be dead. And what about on the other side, if you were to make it colder and colder? So hang on, it should be dead, and then colder and colder, dead. Right, there must be some kind of range that it can only transpire in, and then outside this range can't. So the graph only looks linear for a certain part of its temperature range, and then it's not linear outside of it. So I think whoever wrote this question was imagining the student would say no. Perhaps they could use some of their biology knowledge to actually give a reason of no then. So I would say no, as it's stuck. You can write this down. No, as 30 degrees is too far outside the upper value of 25. I'm just looking at the next one, seeing if it's something you've done. The next one is a chi-squared, I believe, and quite unusual for this chi-squared is that it's 10%, which is actually quite unusual. So if it's a 10%, what column do we use in the table? The 90, okay. Do you want to practice another chi-squared? Yeah, but do the next one there. Oh, good, yeah. Wait. Yes. Okay. In a college, it's estimated that 50% of students fail their driving test at the first attempt. A course which is designed to improve driving skills is provided for students to attend before they take their test. A sample of 15 students who had taken the course and the driving test was selected. It was found that 4 of them had failed, and it's claimed that going on the course reduces your chance of failing. Right, so what would we say is the hypothesis here that we're testing? What is the claim that we're testing here? Yeah, no, go on, yes, sorry. The students who attend the class. Nearly have it, yeah. You have the right idea, but it's just how to phrase it. The way we usually phrase a hypothesis is, I don't know if you understand what I mean if I say this, but we try to maintain the status quo, if that makes sense. So we always state a hypothesis as kind of a neutral. Like, for example, the dice is fair. That's neutral. Because if we said the alternative, the dice is unfair, that's accusing. Do you get what I'm saying? Like a bit like if you were taken to court. Are you guilty or innocent at the start of your trial? Oh, I'd be very worried if I was going to a country and I was guilty at the start of the trial. Are you guilty or innocent at the start of the trial? You're innocent.
Yeah.
This is like the neutral position to take. And then at the end, you are either guilty or innocent. So it's kind of the same thing here. If I was to take a neutral position, what would that be? That there is no effect of the classes. That's actually a neutral position, because it's to say otherwise you're making a sort of an accusation or a claim.
What if you just said the students that take the course with pass their driving test?
That's like making a claim. It's a bit like saying, if you eat my chocolate cake, you will lose weight. Do you know what I'm saying? Like, the neutral position should be, if you eat my chocolate cake, nothing will happen. That's like the neutral position, you know. So the neutral position here is taking the course has no effect on whether you pass or fail. So if we just write that down, taking the course has no, hang on. I'm trying to think if, don't tell me now, if it's an A or an E. Flip. An E, isn't it? Okay. Yes. No, but you can spell it with an E or an A depending on how you're using it. Or is it A? Are you sure?
Yeah.
Okay, I trust you. Taking the course has no effect on the pass rate or the fail rate, the pass-fail rate. Okay. Now, let's do our hypothesis test here. Okay. Expected, observed. What are the two things we can observe? What are the sort of two... In the previous example, there were 4 things to observe. We could get a 1, we could get a 2, we could get a 3, or we could get a 4. What are the things we can observe in this example? Pass or fail. Okay. Pass or fail. How many students took the course? 15. Now, if the course had no effect, didn't really do anything, and you had 15 students, how many would you expect to pass and expect to fail? Yeah, 7.5, and 0.5 is okay here. It's just in the calculation. 7.5 and... Now, why did you say 7.5? Yeah. On average, 50% of people pass and 50% fail. So, if the class did absolutely nothing, then half the people should still pass and half should still fail. Okay, now, on to our observation. How many people did we observe to pass?
11.
Was it 11? And how many did we observe to fail?
4.
And what's the degrees of freedom for this problem? No? Nope. Yeah, one. Because it's the number here, the number of outcomes, I suppose, minus 1. So here we can have pass or fail, so that's 2 minus 1. In the last example, we could get a 1, 2, 3, 4, so that's 4 minus 1. Okay. Right, now before I do the calculation, what are we thinking? The class had an effect or had no effect? I'm going to say no effect, and let's calculate it. Okay, so chi squared equals, so what's the first one? 3.5? Over 7.5. Oh, flip. Excuse my language. I just realised, yeah, no, it's very bad of me. I shouldn't be using such foul language. I realised I wrote the formula down wrong. This is disgraceful. When I square, I only square on the top. And I think in the last example, I had my brackets around the whole thing. Yeah, this is an absolute outrage. If you can fix that, please, in the last example. Yes?
Yeah.
Does that change the outcome?
No, I did it the normal way, not the whole bracket thing.
Okay. Oh, so the number you gave me was actually the right number? Oh, that's fortunate. Okay. Right, anyway, let's fix it up with this one. So I have 3.5 squared over 7.5. And what will be the next one? 4, 5, 6, 7. 3.5 again? 7.5 minus 4? 3.5? 3.5 squared over 7.5. So what's the total? What do we get in total here? $3.66? 3.27 then. 3.27? Okay. Let us see if this is too big or too small. So, to our formula book. Now, actually, just, let's see. Come on. Stuck. Look. Yeah. I was worried that it wasn't in the formula book. I'm sorry. Here it is here. Can you see my mistake? The square is only on the top, not on the bottom, okay? Don't be a Stephen and let that happen to you. Right, on to the last page. Okay, what row am I looking at? Row number 1 we said, wasn't it? And what column?
0.9.
This is it here. Yeah. The critical value is quite small, 0.016. And what did we get?
3.27.
Ah, that's way over. So, reject or accept? Reject. Yeah. Quite clearly, reject. So the numbers are big enough that we think that the class actually had an effect on it. So we reject. Reject the hypothesis. So in other words, we can say that the class had an effect. Now, technically speaking, we're not saying that the class was beneficial. We're just saying it had an effect. I mean, it could be the case that taking the class makes you worse. Yeah.
What happens if you always have to right?
Say again?
For the hypothesis, you have to write it always neutrally.
No. In the exam and in the marking scheme, some people were suggesting writing the hypothesis the other way, that the class had a positive effect. This is acceptable. It's just not usual, but it's acceptable. No, it just means if you stated it as the opposite, that taking the course has a beneficial effect, then obviously you are not saying reject at the end. You are saying do not reject my hypothesis. So it only changes, it's only a vocabulary change. I prefer to write it as the neutral because it means I have to think less at the end. As I dislike thinking, it is better for me this way. Yes. Okay. Are we okay? Yes?
The question is wrong.
Yes? The calculation?
Is this like all wrong? Isn't the answer?
You're telling me that there was a calculation mistake, or you're asking me if there were a calculation mistake?
No, you said we have to.
Oh, in the last part?
No, this one.
Hang on, wait, pause. Firstly, I'm not sure which question you're talking about. So are we talking about this driving question or the previous question about the biology?
At the die.
Oh, okay, way back to the die, right. Yes, let me just go back up here to it. Where the heck's it gone? Oh, here it is. Yes, I made a terrible mistake here. This should have been 4 squared over 25. The square is only on the top. Maybe we'll just recalculate it. What do we get now? What is it? 4.4, is it? Ah, so reject. Okay, congratulations for the people who took the opposite position of me then. You were right in the end then. 4.4 is way bigger. Way bigger. Okay. Yeah. Scroll back down. Yeah. Okay. Right. Where have we gone? There we go. Let me just write this down. What was the critical value in the table book? What was it, sorry? 0. Oh wow. That's very small. So we really have to be quite close here then. Yeah, okay. No, I guess that's actually a bigger difference than I thought. This is a difference of about 3, isn't it? It's nearly 4. This is nearly 4. Yeah, okay. This is the reason we do chi-squared, because you can't judge your personal opinion on whether something's fair or not. So we can see here the class did have an effect on the performance, yeah?
In the coursework, do we have to attach the whole table to our coursework and then
Which table exactly? Oh, you mean like this?
no, like the critical values to
Oh, no. That wouldn't be normal. You would simply say, I got, or the value of the chi-squared was this. However, according to the table book, the critical value is this. Therefore, I reject, or I do not reject. Okay. Anything else on this one? Is okay? Yeah? By the way, I should point out that this table here is actually, whoever made this formula book did a bad job of it, because it's very normal to include a picture here. And you need this picture here to decide which values to use. Anyway, whoever made this, I'm not sure if they have the table the right way around. So I'm assuming whoever made this did the right job. Because you sometimes can use this value.
yeah.
And I can't tell because whoever made the table, I just don't know which one they mean. It would be normal to use this one if they're using the same table I use, but it could have been this one. Do you know what? I better check it for you because you're going to be using this table book. So rather than logging in here, can somebody just go to Google Images and type in chi-square distribution and we can check. The reason I'm saying that there's a mistake here is that what's missing from this table book is a diagram of a bell. And I need to know if these probabilities refer to the left or to the right. Now, I'm assuming they refer to the left, which means I should use this number. If they refer to the right, I should use this number. Let me have a look. It's not quite that one, but let me just go to images here. Yeah. So let me just check. What did we say 0.9 and 1 was? Yeah, this is okay. P 10, 90,
Isn't that
20.
the normal distribution table?
Yes. It is. That's, I swear. 0.9, 1, 2.76. Disgraceful. Disgraceful. Whoever made this table made it backwards, if you can believe such a thing. It's backwards. Yeah, the table is literally backwards. You have the table there. You see the numbers here. The first number is 0.005. Isn't it?
Yeah.
0.01. Yeah. Table's backwards. So, there's no big deal, we can easily fix it. Listen carefully. We use this number.
Yeah.
Yes? No big deal. We have to use this one. Okay, the table's backwards. Actually, this is probably better for you because it means you don't have to think. In the question it said 10%, and this here is 10% then. Does it change our hypothesis, 2.71?
No.
Do we still reject, or?
Yeah.
We reject now, it changes it then. Okay. Can you fix that 2.7?
We don't, no, it doesn't, no, we still reject it, yeah.
We still reject it, fine. Just write down 2.71 as the critical value, please.
Are we gonna get another page for the formula?
Oh no, this is the one for the exam.
in the exam, do we still have to use that as a 10%?
Yeah. Yeah.
So if it's 95%, use 0.05?
In the last one, I should have used this one. Yeah. Yeah.
But it's close. What was the 5% then? Wouldn't that be the 95?
I am one at a time. Right. Have you written down 2.71 for this one? And do we accept or reject? Reject. Right. In the last one, that was the 5% one. I used this value, I believe, but I should be using this one. Still reject?
Yeah.
What was the number like?
No, you would accept it then.
Yeah. It's the opposite. Haha, back to my original suspicion. 7.81, and we got. So in this case, we do not reject, and we think that it is fair.
But this was question, why did you make it?
Okay, hang on. What value did we calculate? 2.2 and 3.2. Okay, and the limit is 2.71. So it's simply, are we more than or less than? So are we more than or less than the limit? If the limit is 2.71 and we got 3.2, above or below? Above. So reject. That's it. It's not. You're thinking about if it's close, it's okay. It's more if we're over, it's not okay. Yeah. Again, this is actually good because it says 10% in the question, so we actually have to look at 10%. So this means we have one less thing to think about. And what have we learned today? Less thinking is better. Okay. Right, I'm glad that's cleared up. Alright, I think we have time to do one more question then. So actually, in the statistics now, the next few questions are the same. We have expected value and variance, we have another average, and so on. Another average, another regression. If you want to practice another chi-squared, there's one on page 39, if you want to do that later.
Can you just teach us the normal distribution?
Yeah.
The one that we just doing before?
Yeah.
On page 36.
The normal distribution. Oh. The good voice is saying, do it, Stephen, and the bad voice is saying, no. The problem is, normal distribution takes 3 lessons. I couldn't properly do it in 10 minutes. It might just make it worse for you because it will be too compressed.
Better than what we
You're making me feel guilty.
If you can show us how to do this question, we'll have an assistant when we do it in class.
How could I possibly say no? Okay, so we'll have a look at the one on page 36 then. Okay. The one on 36. The one on page 36 actually is, there's 2 types of normal distribution problems. One where you have to calculate probability, and one where you have to calculate sort of confidence intervals. Yeah. Now, do you particularly mind which type that we do? It's just that you want to see one of them, or
Just want to see this question.
this particular one? Okay, well, we'll do this one here. So, the mass of certain types of birds are assumed to follow a normal distribution with standard deviation 200 grams. And the mean mass of the birds is 1800 grams. Okay, so how many birds have we got? We've got 40 birds. And their average mass is 800 grams. And their standard deviation is 200 grams. Now, you all understand average and standard deviation. Now, I hope you all also understand that if you were to do a survey, you know, if you were to ask people their height or their weight or whatever, because you wanted to know what the average height or weight in the country was. So let's imagine back home in your home country and you want to know what the average height or weight is, so you survey 100 people. What would be a problem with your results? Like, would your results be reliable? What about if I survey 10 people? Would that be better or worse? Why would it be worse? Yeah, there's a small sample. So what happens as the sample gets bigger? Yeah, the error, or how wrong we could be, reduces. And what we really want to know is, if I'm estimating the average, can I put sort of limits on the possible true value? Okay? Because the true value isn't really 1800, because we only had 40 birds. Perhaps the true value is 1900. So, the way we can sort of put limits on this is by using this formula. I'll change this back to x. So, it's the average plus or minus 1.96 standard deviation over square root n. This part here is called the error. Do you ever notice, or maybe not because you're not maths geeks, have you ever noticed when you look at surveys on TV, at the very bottom of the survey it might say something like margin of error plus or minus 5%? Yeah, congratulations maths geeks for noticing that. Good job. So, how did they calculate that number? They used a formula like this. Okay, so let's calculate it here. We have, what have we got here? 1800 plus or minus 1.96, 200 over root 40. Now, can somebody just tell me what this part is here? Just this whole fraction here.
Sorry, what's that part of the margin of error?
Yeah, it's the error. There's a couple of different terms for it. I just call it the error, but it's margin of error, standard error, but basically the error. What did we get there? 98, so 62 then. So what is this telling you? This is telling you that the true mass of the birds is 1800 plus or minus 62. So in fact, maybe the birds could be as heavy as 1861 or 1860. Do you understand? Like, it's sort of it puts limits on our estimate. This is called a confidence interval. Now, I believe this formula is in the formula book. Where is my stupid cursor? Let me see if I can find it for you. Whoop. There it is. Can you see it? That's the confidence interval. Now, you can see it's just a formula. You have 1.96 here. The reason it's called the 95% confidence interval is because it's still possible we're wrong. Perhaps the true mass is something like 2000. So, why do you think it's called the 95% confidence interval? What do you think if you think about the meaning of those words, what do you think? Very good. You're taking the legal point of view. Yeah, so what's the meaning of 95%? How can we explain that? Well,
95%
yeah.
realistic.
Oh, started off so well. What do you mean by realistic?
Reliable or...
Yeah. Basically, you're saying, what did we get? 1700? What was it? 1800 plus or minus 62. We're saying that I'm 95% confident, the 95% chance that I'm right, that the true mass is within 62 grams of 1800. But I'm not saying 100%, so I don't get sued. So there's a 5% chance that it's outside of this range.
There they give plus or minus? Do we have to actually find out the minus value and the plus value?
It depends. I personally, like if a student wrote down what I wrote with the plus minus 62, I would give the mark. But let me just see the words. If you, because they said confidence interval, I think it's okay. Now, if they said something like, you know, what are the two ends of the confidence interval, then maybe I would actually calculate the two. Who are the two students I have for Charles? You two, great. So we'll take, of course, a little break, not for you, but me, because I need it. And then my plan is to run through whatever questions you feel you can't really figure out from the sample papers. You have the sample papers?
Yes.
You have them on your phone?
Yes.
So, have you got a chance to buy them? Or, yeah, so you have a list in your mind of what, yeah, okay, good. So, get a cup of coffee and then we'll run through those Charles ones.